Our next speaker is Professor Stella Vosniadou. She is the strategic professor at the Flinders University in Australia. And her expertise is mainly on the developmental psychology in learning. And in 2011, she received the Distinguished International Contribution to Child Development Award by the Society for Research in Child Development. And last year, she became the Fellow of Academy of Europe. So I think it's your time. You got the floor. Please join me to welcome Professor Stella Vosniadou.
Well, thank you very much, Mei Hang, and thank you for inviting me to be a keynote speaker in this conference. And I hope that I will contribute to the subject that Miki started, because we have many common things with Miki, except that I'm looking at things more from a cognitive developmental point of view, because I'm a cognitive developmental psychologist, and I like to understand how things develop and how children develop their learning of science. So the argument I'm going to make today, is that we have not actually paid enough attention to students' initial concepts and the influence they exert on science learning. That initial concepts are not replaced, but coexist with scientific ones and influence their construction and employment. And that we need to develop better curricula, instruction, and assessments that use learning progressions and help students overcome the cognitive obstacles that are posed by initial concepts in their process of science learning. And an overview of what I'm going to talk about, I'm going to give you first a quick description of how I see the process of learning science, again from a developmental point of view. Then I will present some experimental evidence that shows that initial concepts coexist with scientific ones and influence their construction and their employment. And at the end, I will draw some implications for instruction. So, again, I'm going to start with a thing that was also the beginning of Miki's talk, the importance of misconceptions. It's almost 40 years now since Driver and Easley, in their seminal paper, drew attention to the fact that students have preconceptions, alternative conceptions, misconceptions that influence the process of learning science. And since then, we've been trying to understand what these misconceptions, preconceptions are, and how do they influence the science process, and what to do about them. So although there is really wide agreement that these misconceptions or preconceptions exist, there's still quite a lot of disagreement about what they really are. So there are at least 3 points of view that are dominant. One is that they're accidental errors, they're cognitive biases. One is that they're P-primes. This is a view that has been supported and defended by Andy DeSessa, who says that they are simple subconceptual elements that originate from superficial interpretations of physical experience, and that the process of learning science is a process of collecting these simple and subconceptual elements into more coherent kinds of theoretical frameworks as students are exposed to science learning. And then there is another point of view, which is the naive framework theory point of view, which is what I'm going to defend in this talk today. So according to this point of view, P-primes, like the ones that DeSessa is arguing for, might actually be present, but are organized within larger explanatory system of naive physics from early on. So this is what I claim. So my basic difference is that the need for explanatory coherence is not something that children need to be taught by learning science, but it's something that is an important characteristic of our cognitive system. and that it's an important aspect of our human existence, because if we don't have the need for explanatory coherence, we're not going to be able to survive. We need to build theories before we go to school and are taught science. So even though I think that the notion of the P-prime is a good idea, I think that these P-primes are organized into larger wholes that I call framework theories from early on. For example, let us take a P-prime like what Disesa calls Ohm's law, Ohm's P-prime, which is that more effort produces more effect. Now, there could be a P-prime like that, but it doesn't exist in our conceptual system, even in the conceptual system of a young child, isolated, because you need to have an idea that effort can be exerted only by animate agents. Effort is something that animate things do, and therefore you need to be able to distinguish animates from inanimates, and so on. So what I'm claiming is that from the very beginning, there is a larger framework that provides, which I call the framework theory, that provides some coherence to our kinds of experiential concepts that are produced from being in the physical world. So framework theory is a skeletal conceptual structure. The grounds are deepest ontological commitments. It's not explicit, it's not well-formed or socially shared. It's not subject to metaconceptual awareness. It's not systematically tested for confirmation and falsification. So it doesn't have all these things that make scientific theories, but nevertheless, we have chosen to call it a theory because it is a principle-based system which is characterized by a distinct ontology and a causality and can give rise to prediction and explanation. So, for example, the claim is, and this is based on research with very young children, even with infants, that from very early on, children make a fundamental distinction, for example, between naive physics and naive psychology. And how do we know that these are two different domains? Because they have a distinct ontology. And what do we mean by ontology? We mean that they're mechanisms that children use to differentiate the kinds of entities that belong to the category psychological beings versus the kind of entities that belong to the category physical objects. And some of these distinguishing characteristics is, first of all, a self-initiated movement. From very, very young on in infancy, children understand that there are some things that move by themselves, that also talk, smile, do things, and then there are other things that don't, and that you have to push them and pull them. So they categorize this. So these are some important characteristics that distinguish the entities that belong to one category versus the entities that belong to the other category, psychological beings versus physical objects. And that we know that by the end of infancy, by the age of 2, there is also a well-developed causal explanatory framework that explains the behavior of psychological beings in terms of their intentions. We call it intentional causality. So the behavior of people is explained on the basis of their beliefs and of their desires and of their thoughts, whereas the behavior of physical objects is explained in terms of mechanical causality by the push and pull of other objects or of other animate agents. So from the beginning, you have these different kinds of framework theories that distinguish entities and causalities that belong. So because of this connectedness and because there are principal kinds of characteristics that differentiate the entities from one domain from the other, the causality that goes with it, that's why I call them framework theories. Okay, so these first ontological categories are not wrong. So there are a lot of similarities here between what Miki talked about and what I'm talking about. So Miki talked about different ontologies and how sometimes they clash, that we categorize things in one ontological category, whereas they should have been categorized in the other ontological category. I agree with that, but I'm interested more in understanding how these ontological categories develop, what it is from cognitive development that makes children create ontological categories that later on they will find come in conflict with the scientific categories. So these early ontological distinctions are not wrong as far as I'm concerned. They're based on the simple interpretation of everyday experience, and they're constantly reinforced by this experience. And this is why I think it's so very hard to really get rid of them. And I will argue here that we never get rid of them. They're there, and I will show experimental evidence that they continue to be there because they're constantly reinforced by experience. And they're actually useful in getting along in the everyday world. Now, years of scientific discovery have drastically altered our explanations of physical phenomena and our representations. And learning, therefore, science requires fundamental conceptual changes in students' ontological and epistemological commitments. It requires the creation of new ontological categories, new representations, new epistemic understandings, new forms of reasoning. And this is not easy. It's very difficult. Okay, so let me give you some examples. For example, let us look at the concept of matter. The initial understanding, the framework theory of matter, is that physical objects have a permanent existence. You can see them, you can touch them, you can feel them. This is a perceptually based theory. And all of these beginning theories are really perceptual based because they're created by the children in their attempt to explain their experience. Okay, so the first theory of matter, we have a lot of evidence from studies even as early on as the 90s by Stavy, by Carey, by Carol Smith, by Marian Weiser, that children have the perceptual-based theory of matter and that they distinguish physical objects from, let's say, mental objects, ideas, on the basis of whether you can see them, you can touch them, you can feel them. And on the basis of these, they categorize solids and liquids as matter. So this is a connected network of concepts, a framework theory. Now, as they're exposed to science teaching, starting very early on, or even sometimes to experience to science concepts from their parents at home or from other children. Okay, they start, for one change, one conceptual change, is to think of air as matter. Now, thinking of air as matter is a conceptual change because it requires that you alter your understanding of matter, because air is not something you can see, hear, or touch, or feel. Okay, so once you understand that air is matter, then you've made a big conceptual change. And you've changed your ontology, you've changed your criteria for deciding which entities belong to the category matter. So instead of being a perceptually based theory, now you need to enlarge this theory, your criteria, and classify as matter something that has weight and occupies space. Okay, so much larger ontological changes, of course, are required when you are exposed to the atomic molecular theory. You have to understand then that matter is made of atoms, atoms can be joined to form molecules, etc., and these are huge ontological changes that need to happen. Okay, so let me give you another example from an area that I have researched a lot, the concept of the Earth. So children think of the beginning that the Earth is a physical object that is stable, stationary, and grounded, as opposed to astronomical objects like the sun and the moon that are up in the sky and they move, etc. And there are a number of conceptual changes that need to happen as science is taught and children are exposed to scientific information. And these changes are slow and gradual, and they have an order of acquisition. Certain things happen before others. So, for example, children first learn that the Earth is a sphere in space. Now, this is a big ontological change because it's not a physical object versus an astronomical object. The Earth is an astronomical object, and this makes, of course, changes in the concept of astronomical object itself. They have to learn about the heliocentric solar system, whereas at the beginning they're geocentric. They have to understand how the Earth and the planets move, how they evolve and rotate, have to understand day-night cycles, seasons, etc. So the changes, the conceptual changes that need to happen are changes in ontological categories. So before they had this category physical object, where the Earth was a physical object, and the astronomical objects. Now they're astronomical objects, and they distinguish between the sun, the planets, the satellites, etc. So these are changes in ontological categories, changes in representation. So at the beginning, the representations they have are based on their experience. So their experience teaches them that the Earth is kind of a flat ground and that the solar objects are in the sky. The sun and the moon move and they create day-night cycle. Whereas by the end of and we have experiments here that show that this is the case, that young children, when they enter elementary school, have this type of representation. We ask them to draw, we ask them all sorts of questions. By the end of elementary school, they have this type of representation. And the second type of representation, which is closer to the scientific one, is really an abstract model that has a very complex relationship to what it represents. Whereas children's early representations have a one-to-one relationship to the world that they depict. Models, scientific models, have a very, very indirect relationship to what they represent. And this is why model-based reasoning is difficult. And it's something that it needs to be done systematically in order for children to understand how these models work and what they represent and what is their relationship to the first models that they make, okay? And how you go from one to the other, not just understand them as abstract things, but understand the relationship to what they represent. And then there are also changes in personal epistemology that need to happen. So the children have to learn to go beyond appearance. They have to learn to question appearance, to understand the constructive nature of knowledge, to understand that their beliefs and explanations may be false, that they need to be tested, that explanation is based not on the simple interpretation of sensory evidence, but on hypothetical and observable entities. They have to learn how to reason with models. And they have, of course, to develop processes of evidence evaluation, hypothesis testing, problem solving, and reasoning. And these are all very complex things that instruction needs to provide. Okay, so this is a slow process of developmental change. And in this process, you have the creation of fragmentation and misconception. So from my point of view, fragmentation, it's not that you go from one complete theory to another. I think the theory point of view has been misinterpreted by saying that you go from one consistent theory to another consistent theory. No, this is not the case. What I'm saying is that at the beginning, you have these skeletal theories that we call framework theories or naive theories, that the process of change is a slow process during which you create fragmentation and misconceptions. And the process of creating misconceptions and fragmentation is the same, and it has to do with this idea of assimilation that Miki brought up in her talk earlier, and there was some questions about it, that we have prior knowledge, we have all these categories that we developed on the basis of experience, children have. So when new information about science, scientific theories comes in, and this information is very contradictory to what we already know, it's not possible often to understand the scientific point of view. So in the process of trying to be constructive and to relate the scientific information to what you already know, you can fragment your framework theory, or you can create hybrids. You know, you can try to connect one thing to the other, creating misconceptions. So, for example, I'm going to give you an idea of some examples about what I'm talking about. So these are explanations of children's day-night cycle. So the original explanation of the day-night cycle that you get before children are exposed to science is that the sun, the moon go down behind the mountains, or they go down in the sea, or they go behind clouds. But the idea is that the Earth is some kind of stable ground, and then the sun and the moon, the solar objects, move, and they hide behind different objects, mountains, clouds, etc. They go far away. So these are the kinds of explanations that you get. Now, when children learn that the Earth is a sphere in sky, then they start using the same mechanism, which is that the sun and the moon go down behind the mountains, but this time the sun and the moon go down to the other side of the Earth. So you get explanations like the sun goes to the other side of the Earth and the moon comes up. Then in the other example down there, you have actually two different models. One is that they learn about rotational movement. Revolution, they learn about actually the sun and the Earth revolving, but they misinterpret it. So they think the Earth is stationary, and the sun and the moon revolve around the Earth. So instead of going up and down, the sun and the Earth now revolve around the Earth. Another more advanced model is that the sun and the moon are located at opposite sides. They're stationary, and it's the Earth that moves, because now they've learned that the Earth moves, and the Earth rotates, and they think that the Earth rotates up-down, and when we're up, we face the sun, it's day, and when we're down, we face the moon, it's night. And this is a very, very common misconception that you find even in adults when they explain the day-night cycle. So I'm not going to explain the other. Well, the other one is another model where children think that we live inside the Earth, and that the sky is like a dome that covers it. And they picture the sun to be on one side and the moon to be on the other side of the dome, and the Earth rotates left to right, and you go from the sun to the moon, and that's how day-night happens. So you can see these are misconceptions, but they're really fantastic synthetic models that show the attempts of the children to create some coherence out and to relate, to bridge their prior knowledge with the scientific information. Okay, so from my point of view, they should be treated as sources of information for what children already understand and what they don't understand, so that teachers can provide the missing information so that they can go from the synthetic model to a more complete understanding. Okay, now, so this was actually the background. I've talked about these things for many years. It's a theoretical framework that I've been developing for many years. The latest work that I have been doing is this issue of the coexistence of initial concepts or theories and scientific ones. So for many years, what we tended to believe in conceptual change research and in science education is that conceptual change is some kind of restructuring, and once you learn the scientific concept, somehow the scientific theory replaces the naive physics. The coexistence view is a different view that says that scientific concepts do not replace the initial concepts or the naive theories, but the two coexist, and that the naive theory coexists with the scientific one. Now, there is some evidence that this is actually recent research, although there were some people like Guillo Hadano and Silvia Caravita who had raised these possibilities. We had never really investigated this issue experimentally. It started a few years ago. So there is two kinds of evidence, where there is developmental evidence that shows that children, for example, or even adults, often give contradictory explanations. But there's also reaction time studies with college students that show that college students are more accurate and faster in verifying scientific statements when they're consistent with naive theories compared to scientific statements that are inconsistent with naive theories. This is research by Staltman and Vercarel. And also there are results from brain imaging studies that indicate differences in brain activation in experts and novices when they evaluate counterintuitive stimuli. So what happens is that the experts actually, in the case of the experts, you find activation in areas of the brain that are related to inhibition that suggest that the experts are inhibiting the contradictory stimuli that the naive theory, let's say, or the misconception that is interfering with the scientific response. So I'm going to present my work in this area. In order to investigate this problem, I devised 2 tasks that I call conceptual understanding and conceptual change tasks. One is a re-categorization task, and the other is a sentence picture verification task. They're both computer-based tasks, and they're reaction time. Okay, so in the re-categorization task, the participants are asked to categorize concepts under 2 conditions. In one condition, which I call the initial categorization, the participants have to decide between an initial category and an anomalous category. And in the second categorization, the scientific categorization, they have to decide between an initial category and the scientific category. So in both cases, the task demands are the same. So, and there are 35 concepts from physics, biology, chemistry, and math. Okay, so here's an example. The participants are presented with a concept, a target concept. So this is an example from mathematics. It's 1/4, and they have to decide whether 1/4 belongs best to the category on the left or the category on the right. Okay, so this is the initial categorization condition. You can see that the numbers in one category are fractions, and in the other category they're not. They're natural numbers or integers. Okay, so what do you think is the correct categorization here? Anybody? We give this to children that are... Okay, fraction. Here is the scientific categorization. Here, it's the same target concept. In one case, you have the same fractions, and in the other case, you have items. Some of them are fractions, some of them are not, but the idea there is that this is a better categorization because the items in the other category have the same value as 1/4, okay? Now, the claim here is that you need conceptual change to answer this question because it requires being able to understand the value, to compute the value of the fraction, and computing the value of the fraction is actually quite a challenging task. I've done a lot of work on fractions, and there are a lot of difficulty that children have in computing the value of the fraction, and it requires going against your natural your concept of natural number. You have to understand a new symbolic representation, the 2 numbers, you have to understand what they mean, and there's a long process of developing understanding of fractions. And not only that, not only they have to compute the value of the fraction, but they have to understand that different symbolic representations can actually denote the same number, which is quite a counterintuitive notion, because in the case of natural number, different symbolic representations, different numbers denote different numbers. So you have 1 denoting 1, 2 denoting 2, whereas with rational numbers, you can have different symbolic representations that refer to the same number. Okay, so these are quite counterintuitive things, and this task actually is not an easy task. Okay, so this is, you understood what is the initial versus the scientific categorization. And here is water. Water can go with milk, Coke, lemonade, because it's a liquid. versus non-liquids. Here it goes with ice, vapor, and snow, where not liquids, because although they're not liquids, they're the same kind of thing as water. So the items were from physics, from chemistry, from mathematics, and from biology. And we used 593 students from 4th grade, 6th grade, 7th grade, 9th grade, and university undergraduates. Testing took place at the school computer lab, 30 minutes each. Tasks were presented using the E-prime in a single block in a predetermined order. There were mixed initial and scientific categorizations, and the participants were asked to respond as accurate as possible and as fast as possible. And the hypotheses were that you would have greater accuracy for the initial compared to the scientific categorizations, and faster reaction times for initial compared to scientific categorizations. And that's what you find. So the line, the blue line shows initial categorizations that are much more accurate than the scientific categorizations. And you can see what is interesting here to see is that although the scientific categorizations, the red line, that you can see that accuracy increases with age, even in the case of the college students. They have much more accuracy in the initial categories than in the scientific categories, which means that even the college students are really low in terms of their scientific knowledge, okay? Okay, so accuracy was greater. So accuracy was interpreted as a measure that the participants had constructed the concepts in question. More accurate responses for initial as compared to scientific categories. And although the scientific responses increased with age, the accuracy of these responses was still rather low, which shows that even the university undergraduates operated with a conceptual system based much more on initial rather than scientific concepts. Now, this was research that I did when I was a professor at the University of Athens in Greece. It's with Greek students, and the undergraduate were first-year students in social sciences. So maybe if you had more science-oriented people, you would find better responses. But it's still really disturbing to see that college students are so low in their science knowledge. Okay, so these are the reaction time studies, and the blue line is the initial categorization, and you can see that they're faster with the initial categorizations than with the scientific categorization, but you see that the difference is the same. So although reaction times go down, but not in the case of the college students who seem to be taking more time to decide. There is a constant difference in reaction time between the initial and the scientific representation responses that show that the initial responses are much faster, they're easier than the scientific ones at all age levels. Okay, so that's what it says here. The other task was a set and picture verification task. How much time do I have, Meihang? How much time do I have? 5 minutes more? Okay, well, I have to really go very fast. So here we had 4 cases. We had items that were consistent with naive theories and items that were inconsistent with naive theories. I don't have much time to explain. Let me show you just an item that shows the inconsistent items. The inconsistent items here, for example, says it turns night because the sun goes behind the mountains. Okay, this is a theory, an explanation that is true for the initial theory, but false for scientific theories. So it's an inconsistent item and it's false. And we call this the positive misconception. So if children say yes to this item, they have a positive misconception. It turns night because the Earth turns around itself. This is false for the initial explanation, but true for scientific theories. And so this is inconsistent. The initial and scientific are inconsistent, but it's a true item. And if students are wrong here, we say that they have a negative misconception. They say that the scientific explanation is wrong. Okay, is that clear? So what you find, the results, show that the green line shows the responses that were consistent with a naive theory, that are much more accurate than the red responses that show the responses that are inconsistent with the naive theory and consistent with the scientific one. But you can see here, there is a difference in the red lines. The positive misconception is the one at the bottom, is much more common this shows less accuracy than the negative misconception. So what does this mean? It means that the participants, and the participants were the same, fourth graders up to all the way to college students, are more likely to accept as true the scientific explanation. So their science learning grows. This is the red line on the top, where it says that science learning increases with age. However, they're still accepting the false initial theory. So they're holding, as they're learning science, they still hold on to their false initial theories. Okay, so they have, okay, and in order to show this bit better, I've done this, and again, here the blue line shows how science learning increases, and the light blue line shows the acceptance of the false initial theory. And you can see that there is no decrease in the likelihood of accepting the false initial theory until about 9th grade. Okay, so although through the primary school years and middle school years, students are learning science, they're still holding on to their naive conceptions, okay? So this is really, I found this a fascinating finding, because it shows that students continue to hold their initial theories, their false initial theories, even after they have learned the scientific ones. And it's only after 7th grade, 9th grade in university undergraduates, actually not the 7th grade, it's the 9th graders, that we see a decrease in the acceptance of the false initial theory. So this is evidence that these two theories coexist. Now, it's possible that the participants do not understand the contradictions involved in holding two inconsistent theories. It's like saying, it's both the Earth rotates, and also the sun goes behind the mountains, like holding two contradictory theories. Or they may create some hybrid conceptions, like the ones that I explained before, that try to explain that. Okay, my time is running out, so I'm not going to give you more about that. There are important theoretical implications of this, and if you ask me a question, I can tell you more about that. But for instruction, I think that if I can quickly show 4 slides that show the implications. First of all, I think that that we have underestimated the influence of naive physics or framework theories or initial concepts, whatever you want to call them, on science learning. And usually what we do is that we do the cognitive conflict kind of instruction, where we alarm students, we tell them that your prior conceptions are wrong, and here learn the scientific one, but that's not enough, okay? And I know that many people are concerned that if you do discuss misconceptions in the classroom, maybe that would reinforce the misconception instead of the correct response. But I think these results are giving us information that says the opposite, that it's actually important for students to understand. First of all, many of these naive theories are implicit. People are not aware of them. It's important to discuss them, to bring them to awareness, so that the children and the students understand the contradictions involved between one framework and the other, but also stop seeing them as contradictory and understand that these are different perspectives, and understand how they relate to each other, and understand how the scientific model provides an explanation that is more explanatory adequate and more advantageous than the... So these things really need to be discussed. I think we put them under the carpet, and we think that if we don't discuss them, and if we just talk about the correct scientific explanation, we're solving the problem. But I think results like the ones that I showed you show that we don't, that these naive theories are there in the background and we're not dealing with them, and they're creating inconsistency and confusion. So use collaboration, discussion, argumentation, inquiry setting to encourage students to express their ideas, learn how to revise them, create bridges between everyday and scientific concepts, instruction that is persuasive and explains and justifies, not just making claims. Now, using learning progressions to have instruction that is based on student needs, and something at the bottom that I think learning progressions have not done very well, understand where cognitive obstacles were. Cognitive obstacles occur at the places where our naive knowledge or naive theories conflict with a scientific concept. Stop here and explain to students what, how to deal with that. Develop strategies for conceptual changed learning, like the ones that Mickey was talking about, comparing, contrasting, using analogies, using metacognitive monitoring, learning how to inhibit a previously learned response and be reflective so that you have enough time to consider an alternative response, shifting between one response and the other. And of course, deliberate practice. And finally, this recent evidence that we have shows that there are important individual differences in science learning that may relate to cognitive characteristics of students. For example, a lot of talk is now being made about spatial reasoning and how spatial reasoning is important for science learning. Is it spatial reasoning? Is it analytic reasoning? The results that I have mentioned, although I didn't have the time to go more deeply into the theoretical implications, show that executive function like inhibition and shifting and working memory are very important in learning science. We need to understand these cognitive characteristics of students more and maybe design early interventions that help students become more cognitively flexible. Okay, I think that's all. Before I finish, although now I'm a professor at the university, at Flinders University in Australia, this work was done at the Cognitive Science Lab at the University of Athens, and these are some of my students who have contributed, and I want to thank them. Thank you very much. Thank you very much.
That was very enlightening. Thank you very much for the talk. So we have very few minutes, but I still like to have some reflections from the audience. So any hands? Any questions for Professor Vosniadou? I think the theory of, please. Framework theory is really helpful, yeah. Mary?
I have a question, and that is, you didn't share with us, or at least I missed it, who were the participants in your study? So my question is, how did you take into consideration the language of the students, the cultures of the students, in making the examples that you used for your study?
My study was done in Greece. The language was Greek. The students were students in Greek primary schools, secondary schools, and universities. We didn't select them. It was just in the schools that we found, the schools were middle-class schools. And the science topics and areas were the ones that are covered in the Greek curriculum for science learning.
So my question is, if these students were middle class, do you think you would have found the same thing if you had gone to schools in which the students were not middle class?
I think we might, what we find is that we may get even worse results in the sense of less science learning, but I think the trends would be the same.
The last one.
Yeah.
Hi, I'm Francesco from Italy. I was thinking that the coexistence of different ways of explaining the world is not a phenomenon that we only find in students as they evolve conceptually, but it's actually a structural part of science itself. As a physicist, of course, you can use Newtonian approaches and forget completely about relativity or quantum mechanics in specific context of application. So I was wondering if in teaching to students, if it is also important to say that it makes sense to have different conceptions of the world,
Yeah.
and it depends of maybe which context,
Yeah.
which theory is most appropriate.
Well, thank you for the question. It's very relevant because I think that's what I've been trying to say. That I think that in science teaching, we've been saying that the science point of view is correct and your misconceptions are incorrect, okay, and correct them. And often we don't want to even talk about the wrong things. But what I'm saying is really we need a different perspective. We need a perspective where the naive theories are really valid interpretations of the world from the point of view of our everyday experience. It's a kind of an egocentric point of view, it's perceptually based, but it's very valid and it's very useful in everyday life. So we need to learn to take different perspectives and understand the scientific perspective as a different perspective, which of course is better in the sense that it's more powerful, it's more, it has greater consistency, it's a valid theory, it has been tested, but to understand that there are different perspectives and to be able to go from one to the other rather than saying one is wrong and the other is. Yeah.
Okay, so
David, you have a question?
Yeah, I was wondering the recent results showing that students don't lose their naive conceptions; they just sort of inhibit them,
Yeah.
even in scientists. I'm wondering how that interacts with your theoretical perspective of framework theories. How do you make sense of that from a framework theory perspective?
What do you mean that the framework theory continues to be there? It raises also questions about representation of concepts. How are they represented? Are they represented at different levels? Why are students not aware of the inconsistencies? Are they represented in different modes? Are they represented in different layers? It raises lots of questions about memory representation and how it is possible to have these, different frameworks. And also it raises also questions about processing. For example, there are similarities to dual process theories that claim that there are two kinds of processes. Type 1 processes that are more fast and automatic and less explicit, and type 2 processes that are more reflective and more difficult and require more time and more working memory. Or it raises question about additional resources of the cognitive system. For example, it shows that science learning requires the activation of prefrontal areas that are involved in inhibition and in sifting. And this takes more time and it's more effortful. So it raises all sorts of questions about basic research that would need to be answered. Yeah.
Time is up. Time is up.
Huh? Time is up. Sorry.
Yeah, sorry about that. But I know we have the sessions coming up soon. So please join me to thank Professor Vosniadou's wonderful talk. Yeah, thank you. Thank you.